Okay, now that we've learned to write reaction ratios, the math is going to go up a notch here, and we're going to use a reaction ratio to find out other stuff. So we have an equilibrium here with, what is this? Ethanol reacts with propanoic acid to produce ethyl propanoate and water. If you're fresh out of Unit 3, you understand how that would make sense. And we can write a reaction ratio for this, Q equals, and because the coefficients are all 1, it's going to be a little bit dull, but let's get it done. Our products are this yucky thing, C2 ethyl propanoate. I'm tempted to just call it EP. COOC2H5 times. Now, I know in the last practice we spent a lot of time throwing out water. Guess what? The water is counted in this reaction, and the reason is none of these things are aqueous. The water here is not a solvent where a bunch of ions are doing interesting things while the water sits there doing nothing. This is a bunch of liquids, including water, all participating in the reaction. In a case where all of the things have the same state, the water is typically included. Water goes in this reaction ratio. I know we probably primed you to leave it out by the way we did the last practices. I'm sorry for that. This is a headache that everybody gets to go through. C2H5OH is one of our reactants. C2H5OH and propanoic acid. Okay, so we've written this equation. We've been doing this for the last few pages, but now we actually have some numbers to go into it. If we are at equilibrium, we know the following things. Our ethyl propanoate, the C2H5, blah, 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 is 2 moles per liter, so that number is 2. The water concentration, don't know. You can write X here, or you can write concentration of H2O, whatever. Ethanol has concentration of 5. Propanoic acid has concentration of 0.10. And generally this Q number can be anything, but if we're at equilibrium, like they say we are, then that means our reaction quotient is this, 2.2. That number is called the equilibrium constant. It's the number at which the reaction will settle down and stay if it can. So when you mix these chemicals, your reaction quotient could start out at 200. If you watch over time, you'll see it go 150, 100, 80, 60, 20, 15, 10, 8, 6, 4, 2.6, 2.4, 2.3, 2.2. It'll come down until it gets to this number, and then it'll go, good. And that's where it'll be at dynamic equilibrium and it'll stay. If it started lower than that, the number will creep up until it gets to 2.2. So always, if you're at equilibrium, you know that this jumble of numbers is going to come out to 2.2. And this is something we can solve. If you think of this as 2x over blah blah equals 2.2, solve for x, how would we do it? You might multiply these together because that's easy to do. 2 times H2O over 5 times 0.10 is 0.5 equals 2.2. Couple things you could do here. You could do 2 divided by 0.5 and obtain 4. That would be reasonable. Or if you want to get the H2O alone, it's divided by 0.5. You could multiply both sides by 0.5 to fix that. These 0.5s would cancel, and you'd get 2 times H2O equals 2.2 times 0.5 is 1.1. And then divide both sides by 2 to get rid of this 2 on the left, and we get that our H2O concentration is 1.1 divided by 2, which is 0.55. concentrations are in moles per liter. Good. Part B, I guess we pretty much covered this. Water is included in this reaction because it has the same state as everybody else. When you have aqueous, 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 and then liquid water, the water is left out. If you have liquid, 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 that means the water should stay in. And you remember in our previous examples, we had gas, 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 and then water gas, as in steam. When the states all match like that, that's an indication that the water should be left in.